All right, let's take a look at what dissolves and what doesn't. Like dissolves like. In the warm-up, it says, in Chapter 6, you learn that chemical bonds between atoms in a molecule can be classified as ionic, polar covalent, and non-polar covalent. There are also attractive forces between molecules that are called intermolecular forces. And for the following substances, list all of the intermolecular forces that are present. So if I'm looking at I2, this is a nonpolar bond, so it's a nonpolar molecule. So this will have London dispersion forces present. For HF, this is a polar molecule. It's a polar bond, and the HF is a special bond that exists in a molecule that is polar, which allows it to hydrogen bond. So this has London dispersion forces and dipole forces and hydrogen bonds. And then we have PCl3, which is a polar molecule, because the PCl bond, if I look at the electronegativity values on the back of my book, that is a polar bond, and it is a polar molecule. So this is going to have London dispersion forces and dipole forces. And then CH3, CH2OH. So since there's an OH on the end of this molecule, that would allow it to hydrogen bond with other substances. So London dispersion and dipole, and hydrogen bonds are present. Now, vitamin A is a fat-soluble vitamin, and it's not soluble in water, so that means it hates water and it's hydrophobic. But vitamin C is soluble in water, and that means it's hydrophilic, so it loves water. And in this section, we're going to explore the reasons why certain substances dissolve in one solvent versus not another. For instance, why does vitamin C dissolve in water but not fat? It has to do with its structure and the types of intermolecular forces that are present in fat versus water. So when we're talking about like dissolves like, that means that a solute will dissolve in a solvent if they both contain similar types of intermolecular forces, and those intermolecular forces are of similar magnitude. So there are three important things for a substance to dissolve. So the particles in the solute have to be separated from each other to go into the solvent. So the attractions between the solute particles have to be replaced. And then the particles in the solvent have to be separated from each other. And those attractive forces between the solvent particles also have to be replaced. And then the solute-solvent particles have to interact with each other. So I'm going to start out by talking about ionic compounds. Let's talk about sodium chloride in water. You know that sodium chloride is held together by ionic bonds, or an attractive between the positive sodium ions and the negative chloride ions. And you have to overcome these forces of attraction between the two ions to get it to dissolve in water. Now, water molecules are attracted to each other by hydrogen bonding. So that means the water molecules have positive and negative ends. So what happens is you have to overcome those hydrogen bonds in between the molecules. Those have to be separated to allow the cations and the anions to move in between them. And the ions become, we call them hydrated. Okay, that means they're going to be surrounded by water molecules, and you're going to replace the attractions between the water molecules with the attractions that the negative or the positive ends of water have for the anions or the cations. Here you see, and we've talked about this earlier, that your cation is surrounded by the negative end of water, which is where your oxygen is. So you have this partial negative attraction between the partial negative end of water with the positively charged cation, and that is happening here for all of these water molecules, okay? On the right-hand side, you have your anion, the chloride ion, attracted to the positive end of water, which is where the hydrogen is. Okay, so this positive end of water is attracted to the negatively charged anion. Now, you know that this attraction is known as an ion dipole force. And that force is similar in size and type to the ionic attractions in the solute and the hydrogen bonds in the solvent. Now, not all ionic salts are soluble in water. We're not going to talk about that in this class, but basically some compounds have ions that are too large for the ion dipole forces to overcome. So let's take a look here at the quick check. Question number 1 says, what is it like between sodium chloride and water? Why do they interact as they do? So sodium chloride has positive and negative ions, and water has positive and negative dipoles. So the sodium ion attracts the negative dipole on the oxygen atom in water, and the chloride ion attracts the positive dipole on hydrogen in water. Number 2, explain why water will not surround I2. What forces have to be overcome between each water molecule? So I2 is nonpolar. So that means it has London dispersion forces in between its molecules. And the water molecules are attracted to each other by hydrogen bonds. So the iodine molecules can't overcome the attraction between the water molecules because London dispersion forces are the weakest of the intermolecular forces, whereas hydrogen bonds are the strongest. So there is no way that iodine molecules can overcome the hydrogen bonding between water molecules and then get in between them. Number 3, would you expect sodium chloride to dissolve in oil, which is a nonpolar solvent? Explain. Okay, I would say no, and that's because sodium chloride is ionic and oil is nonpolar. So they're not like substances, right? So oil is only going to have London dispersion forces, and sodium chloride is held together by ionic forces. So you need positive and negatives that are of equal strength so that they can mix together. Number 4, predict whether sodium chloride will dissolve in ammonium liquid. Draw a diagram to show the forces acting within the solvent, the solute, and the resulting mixture. Sodium chloride is made up of alternating cation and anions. So this has ionic bonds, okay? And then when you're looking at an ammonium ion, which looks like this, you're going to have a partial negative on the nitrogen and partial positives on the hydrogen. And since it has an NH bond, you have hydrogen bonds in between those molecules. So I would scan the QR code with your phone and go over the results. And let's turn to the next page. All right, let's look at a polar solute and a polar solvent. This is ethanol in water. So ethanol is an organic compound and it has an OH group, which is called a hydroxide. And this OH is always on alcohols. That's why ethanol ends in OL. Alcohols end with those two letters in their names. And this is a polar molecule, and it has the ability to hydrogen bond with other ethanol molecules because of the OH bond that's within it. Now, this also has a nonpolar section. So ethanol is CH3, CH2OH. So it looks like this. So here is your OH bond that allows it to hydrogen bond with other ethanol molecules. And this is its polar end. And then it has this nonpolar region of carbon and hydrogens. They call this a hydrocarbon chain. And in this case, the hydrocarbon chain in ethanol is quite small, okay? And if you're trying to see if ethanol will mix with water, well, water's polar. And since water molecules are attracted to each other by hydrogen bonds, and so are ethanol's molecules, that means that these molecules have similar intermolecular force strengths, which allows them to mix. So water and ethanol would be miscible. Now, what happens if the hydrocarbon chain gets larger in different alcohols? Then that molecule becomes more nonpolar. And it's really, really hard for the hydrogen bonds between the larger alcohols to form. So that means the hydrogen bonds are weaker. And so that means that they're going to have a harder time mixing in between the water molecules. So that's why larger alcohols with a larger hydrocarbon chain, that is why they're only partially soluble in water, like butanol or pentanol. And even larger alcohols are completely insoluble in water, okay? Now, what if I'm talking about sugar, like glucose, okay? Glucose has got multiple OH bonds within its molecule, which means it has multiple locations where it can form hydrogen bonds with water. So generally speaking, the more hydroxide groups you have, the more soluble that substance is going to be in water because they are sharing the strongest intermolecular force that's present in water. Now let's talk about formaldehyde in chloroform. Formaldehyde is a polar compound, and they're attracted to each other by dipole forces. And if you look at the next page, formaldehyde's formula is CH2O, and you have a partial negative on the oxygen and partial positives on the hydrogen. So that means that they are attracted to each other by the partial negative end of oxygen being attracted to the partial positive end and the partial positive end of it is attracted to the partial negative end of the other, so they're sort of inverted with each other. You can see that here. And chloroform, just underneath it, is also a polar compound that has dipole-dipole forces. And chloroform looks something like this. Okay, so you've got 3 chlorines bonded to your central atom, and then you have 1 hydrogen bonded to the central atom. So this is a polar molecule as well, and you will notice that chlorine is more electronegative than carbon. So you have the bond dipoles pointing in this direction, which means you have a partial negative end here and a partial positive end here. So you have this attraction between the partial negative and partial positive end of the molecules, and these are your dipole-dipole forces. Now, since you have similar intermolecular force strength between chloroform and your formaldehyde molecules, that means that formaldehyde is soluble in chloroform. Let's take a look at the quick check here. Will ammonia dissolve in water? Well, ammonia is NH3, and it has the ability to hydrogen bond. So I would say yes. They are like substances. They both have hydrogen bonding. So they have similar intermolecular force strengths. Number 2 is ethanol soluble in hexane. Well, hexane is a very long carbon chain. It's got 6 carbons, and then it's got hydrogens coming off of all of those carbons. So this is a very long, nonpolar hydrocarbon chain. So if this is nonpolar, that means it only has London dispersion forces, whereas ethanol, which was CH3CH2OH, it has the ability to hydrogen bond with other ethanol molecules. That's its strongest intermolecular force. And this hydrocarbon chain region is relatively small, so that's its only nonpolar region. So since this has hydrogen bonds as its strongest intermolecular force, and this only has London dispersion forces, the answer would be no. Ethanol is polar, and your hexane is nonpolar. These are not like substances. They do not share similar intermolecular force strengths. Number 3, which is more soluble in water? C2H6 or CH3OH? Well, CH3OH has the ability to hydrogen bond because it has an O bonded to an H here. So that is why it will be more soluble in water, which also hydrogen bonds. Octanol has the formula C8H17OH. Explain why octanol does not dissolve in water. Well, octanol has a really long hydrocarbon chain. I don't need to draw in all these hydrogens to convey it to you, but you get the idea. So here is the insanely long hydrocarbon chain, and it is very nonpolar. The large nonpolar part of octanol is not able to get between the water molecules and overcome the attraction that each water molecule has for another. So that's why the larger alcohols, which this is, are almost insoluble in water. Okay, let's turn to nonpolar solutes and nonpolar solvents. So iodine is a nonpolar substance, and the only interactions between iodine molecules are weak London dispersion forces, and that happens when the electrons on an atom of one molecule repel the nearby electrons on the atom of another, and you get this very weak temporary dipole, and the two molecules are weakly attracted to each other. Now, carbon tetrachloride is also nonpolar, and that means it only has London dispersion forces. So if I'm trying to figure out if I2 and CCl4 are going to mix, well, since they both contain London dispersion forces, they're only nonpolar, right? And they have similar, their London dispersion force strengths are similar. That means that they will mix uniformly with each other. Now, nonpolar solutes are only soluble in nonpolar solvents. So if I go on to the quick check here, and it says paint thinner is a nonpolar covalent solvent. Is iodine soluble in paint thinner? Well, iodine has London dispersion forces. So does the paint thinner because it's also nonpolar. So that means yes, I2 is nonpolar. So that means that like dissolves like, okay? If you ever go on to take AP chemistry, they will never accept like dissolves like as an explanation for things mixing with each other, so don't ever use it, okay? Number 2, mothballs are made of naphthalene, C10H8. With a mothball, will a mothball dissolve better in water or paint thinner? Well, naphthalene, if it's only made up of carbon and hydrogen, and it's a long hydrocarbon chain, that means naphthalene is nonpolar, and water is polar, and just up above they told us that paint thinner was nonpolar. So naphthalene is nonpolar, and it will mix, or it will dissolve, I should say, in paint thinner because it is also nonpolar. And they would share similar intermolecular forces, which are London dispersion forces. Number 3, a student places 10 mils of water and 10 mils of carbon tetrachloride in a beaker. Solid iodine is added to the beaker. Explain what you would see and sketch a diagram of it. Okay, so if you have a beaker and it has 10 milliliters of water, water is polar, and carbon tetrachloride is nonpolar. I don't know the densities off the top of my head, so I am just going to say that water is going to be here, and your carbon tetrachloride will be here. So they will be in separate phases because this is polar and this is nonpolar. Solid iodine is added to the beaker. Explain what you would see. So iodine is nonpolar. So that means that the iodine will mix or dissolve in the carbon tetrachloride layer because iodine is also nonpolar. So the solid iodine will dissolve in the carbon tetrachloride layer only. And the water layer will just remain colorless and clear. And when the iodine dissolves, it should turn a slight pink, but you wouldn't know that unless I told you. Number 4, Why can a molecule of carbon tetrachloride not come between water molecules? Well, carbon tetrachloride is nonpolar. It only has London dispersion forces, so since it doesn't have similar intermolecular force strength, it cannot overcome the hydrogen bonds in water. So water molecules are attracted to each other through hydrogen bonds, and the carbon tetrachloride molecules aren't able to overcome these attractions. And that's because water is polar and carbon tetrachloride is nonpolar. These are not like substances. Okay, let's talk about a nonpolar solute. I'm sorry, we're on fat and water soluble vitamins. It's going back to the previous page. Okay, the fat in your body is made up of nonpolar molecules that are attracted by London dispersion forces. This is vitamin A, and it has a really long hydrocarbon chain, and that is a nonpolar chain. And then it has this little tiny polar end over here. And despite the fact that we have this little tiny polar end over here, since it has such a large nonpolar chain, that means it is held together by weak London dispersion forces. So that means that vitamin A has the ability to dissolve in fat, okay? And that's where the vitamin A will stay until it is needed. So vitamin A is not water soluble because the vitamin A molecules cannot get in between the water molecules, cannot break apart those hydrogen bonds. What if I'm talking about vitamin C? Vitamin C contains a lot of hydroxyl groups, a lot of OHs. So you're going to see, here are my hydroxyl groups. And that makes this a polar molecule. And since it has a lot of hydroxyl groups, it has the ability to break those or pull apart the water molecules and form intermolecular forces of similar strength with water. So vitamin C is water soluble. Let's talk about soaps. Soaps are an application of the like dissolves like concept. They are made using organic molecules that contain positive and negative ions. And each negative ion has this really long hydrocarbon tail. And this is your nonpolar hydrocarbon tail. And this is your polar head here of your soap. And what happens is a molecule like this is going to act as an emulsifying agent, which means it allows immiscible liquids to become suspended in each other. So what happens is the head, which is this region over here, is going to, that's polar, and since that carries a charge, it's going to interact with the water molecules through ion dipole forces and hydrogen bonding. And this tail, which is nonpolar, is going to dissolve the grease and the oil particles. So the soap molecules are going to clump together so that the hydrophilic heads, the heads that love the water, are going to be pointing outwards, and the hydrophobic tails are pointing inwards, and they create clumps known as micelles, which you likely talked about in biology. The micelles trap the oil and grease in the center, in here, in the nonpolar region. And when you rinse off with water, the hydrophilic outside of the micelle carries it out with the water So your hydrophobic greasy center is now gone.